All right, welcome everybody for this combined CTMP physics colloquium talk. This is in the CTMP style, the first of two talks. The second one will be this coming Friday, and we will have a similar marathon next week with a different group. Our speaker today is Jaco van Zyl, and he is postdoc over in MAM in QGaSLab, and this is not his first postdoc. He's been doing a postdoc before that at WITS, and before that he got his degree over in Stellenbosch. So he kind of did a detour through the country, almost coming back home.
Almost a close one.
And I talked him into telling us a little bit about what he's doing, and today is really the sort of the background introduction meant for all of us clueless people over in the physics department who are not overly familiar with complexity theory. So take it away.
Yeah, thank you so much for the introduction, Mr. Weigert. So yeah, I just want to preface again that this is meant to be an introductory talk. Really, I'll be introducing a lot of the basic ideas of quantum complexity, two different notions, how it's computed. If there are any questions at any stage, please don't hesitate to call me. We can discuss it at length. There's plenty of time for that. So what I've done for today is prepare a set of notes. So I've shared this with Professor Weigert as well. Those of you that are interested are welcome to contact either me or him to get a copy of this.
I can put it up with you now.
Fantastic, that'll be brilliant. Yeah, so I think it unpacks some of the main ideas and some of the questions that are asked in this realm of quantum complexity. Let me really start with the really intuitive idea behind that. So the central problem is you want to be able to quantify how difficult it is to synthesize some desired target state. So you have a target state. Sorry, Dave.
Who's sleeping? Oh, can I watch your face again?
Yeah, you know.
But yeah, so you want to synthesize some desired target state. And what you have at your disposal is some set of unitary operations and some reference state. Think of this as the lab state that you've prepared, and you want to take the system to some desired target state. And in the context of qubits, you can think of this as the 0, 0, 0 qubit, and you want to take it to some non-zero qubit with some set of unitary gates at your disposal. Indeed, a lot of the nomenclature, a lot of the language used in quantum complexity theory takes its names from quantum complexity or computational complexity. So you can really think of the set of allowed gates as being, or transformations, as being a set of gates that you're allowed to act with on the reference state. Once you have this in place, the last thing to just specify is some cost function. So you can think of some gates being more difficult or more expensive to manufacture. So you want to minimize, for example, how expensive it is going to set up this particular circuit. Then your cost function will reflect this. The more expensive gates will be given a higher weight than the less expensive gates in line with this. As you can see, there's a large number of degrees of freedom, big chunk of ambiguity. So you've got the set of unitary transformations that you need to first specify, also a cost function on top of that. So there's a lot of ambiguity. And some of the questions that you may ask is, well, if it's such a catch-all quantity, then it's possible that I can probably compute or use complexity as a proxy for a lot of physical quantities. So for example, in the context of quantum batteries, you can think of the unitaries being sort of a proxy for the amount of charge if you chosen the appropriate the cost function that's captured in the battery, for example. But I'll go for some canonical choices and explain why these are often used choices in the literature. And some questions that will come in mind immediately is, if I give you a set of cost functions or a cost function and a set of gates, and I compute this quantity complexity, what physical information does it contain? What can I extract about the system given that number? And more specifically, can I set off complexity in such a way that I can compute quantities that I can't compute in other ways, or at least I can compute it in other ways with a more greater difficulty. And then finally, if I want a particular feature of a quantum system to be diagnosable, such as,
I think maybe just tell Jeff that he's not muted.
oh, yes.
Yeah.
Oh, sorry, Jeff?
Yeah, I'm just going to mute him. All good.
So if you want a particular property to be diagnosed by complexity, say that I want to diagnose whether a system is quantum chaotic or not, how should I choose the gates and cost function in order to reflect that, to extract that from this quantity? Right, so here's just a very simple example of a cost function that you can define. So think of some set of discrete unitary gates that you have to disposal, U1, U2, U3, U4, and so on. And you can think of the target states that you can build from the reference state as being, take all possible sequences of unitaries, act on the reference state, all the states that you can generate in that way, that is your set of accessible target states. And assuming all these unitaries are equally difficult, equally expensive, you can just choose a very simple cost function to be the number of unitaries that you have to dispose. Of course, what can happen is that to get a particular target state, there are multiple sequences of unitaries that you could foreseeably use in order to get that target state. What you would do in such a case is choose the minimum. So you will choose the path or the set of unitaries that minimizes that cost function, and that is your definition of complexity. So this definition I've written down here is very much in line with what you would do in a quantum computational circuit. I have a discrete set of gates. They act on the qubit in a particular way to give me an output qubit. And the number of gates, I can think of them as the length of the circuit in this case is just the complexity. Now, the notion of complexity that's most often used in the context of many-body physics and many-body quantum systems is not a discrete notion that I've introduced previously, but a continuous one. And it's this notion of Nielsen complexity. So the way to think about Nielsen complexity is that as opposed to some set of unitary gates that you have at your disposal, you have some symmetry group, some continuous family of unitaries that I can act on the reference state with. And any targets that you can generate by one of these unitaries gives you the set of target states in this case. So to be explicit, think of some Lie algebra, some Lie group where you have small n generators. So you would get the Lie group by exponentiating, so there will be n real parameters parameterizing this group. So this is now the set of unitaries that you have at your disposal, and I can now act on the reference state to generate targets. When you act on that reference state, of course, the set of target states are going to inherit the set of continuous parameters. So like the elements of the group were parameterized by these n real coordinates, the set of target states will inherit the same set of real coordinates, also these n. And now I have this manifold of target states. They vary from each other in a continuous way. And on this manifold, in order to introduce a cost function, I can introduce some metric. Specify a metric of the cost function, and the complexity will then be the distance with respect to this metric on this manifold of target states. Right, so before I introduce two examples of
Just
matrices
a quick question right here. You can of course do this in very different way. You can take a geodesic distance going from the unit element or from your original state geodesically to where you want to go, or you could put it together from factors and going zigzags, right?
Absolutely.
Segmented geodesics.
Yes.
Any preferred choice or something?
You would just look at two paths that would minimize the distance. If that distance is equal, then I would say you could choose either. Then it would be, and in fact, that would be something like a conjugate point in the manifold, where there'd be multiple geodesics connecting those points. Either of those distances would give you the value of but yes, absolutely. On this manifold, there are many possible ways to go from reference to target state. Yes, you would choose the one that would minimize the distance. Secondly, yeah.
So you would go geodesically, preferably.
Absolutely. And if you read something like a conjugate point, then there will be multiple geodesics, but then you can choose either. Now, one key property of these metrics that I just want to highlight is the following physical property. And it is if I give you two states on the manifold, and on this, so I active a group element, and it's foreseeable that I generate two states, but that I differ only by an overall phase. So e to the I phi, and that phi can be dependent on the specific group element. Do I take these to be two distinct states when I specify the cost function or not? The one I simply prefer to use is to think of two states that differ by an overall phase, contains the same physical information, same probability distributions, they're not distinct. But you can, in principle, specify the cost function to account for that phase as well, to give you a different point on the manifold and have a different geodesic distance connecting it. Now, the set of group elements that give you this overall phase, I'm going to just call these from the subgroup H, and this is called the stationary subgroup of the state. Given a particular reference state and a particular group, there will be some set of group elements, the stationary subgroup, that will act on the reference state just to give you an overall phase. If you choose a cost function that does not map these two states to different physical states, you would factor out that subgroup. And so the group that you're considering is not the big group G, but G factoring out that stationary subgroup. And this is then the group manifold that you're using, and the geodesic distance is on it. With respect to the yes.
Is D here? So I see D of H and D of G. Is D here the representation?
Exactly. That will be the representation. I will typically think of unitary representations.
Okay. So any unitary representation.
Yes, so the representation labels will be important, as you'll see in the subsequent expression. So in other words, if you think of a particular representation, there's a certain number of states in that representation, and that will affect the ultimate value that you get for the complexity representation. So the representation will also be important. Right. So as you can see, so in this example here, I have a stationary subgroup that has n elements, and now I had a group labeled by small n elements. The stationary subgroup factored out is going to reduce that by n. So I'm now going to get n minus n real parameters, parameterizing this manifold of physical states, manifold of target states of the can exist. And the way to think about this is that yes, you have group elements that can add this additional phase, but it's just adding an overall phase. This is an array on the manifold. So you have this manifold G factor out H, and any element of this stationary subgroup is just going to move you along the array, but it's not going to increase the distance that you need to move. Right. So you're in other words happy to reach the state up to an overall phase in the one setup. Right. Now, often what you'll see in the literature is that there's a circuit parameter that's introduced, running from 0 to 1, as you vary this unitary from the identity to the group element that maps you to the desired target state. Right. Now, the Nielsen complexity is now defined as the distance, the geodesic distance, and for that we need to specify a metric. Now, two commonly used metrics are this F1 cost function and this F2 cost function, or the Fibonacci metric. Now, the F1 cost function is just this combination of the unitary. So you would take a derivative of the unitary with respect to S. Think of that inner product with the unitary parameters S prime and S. You take a derivative with respect to the S coordinates and then set S prime equal to S afterwards and take its absolute value. And that now gives me a positive definite metric on this manifold. But this one is sensitive to the overall phase. So there will no factor group that's formed here. The second one, this Fibonacci metric, is this different combination. Here I'll be taking two derivatives with respect to the unitary. So one with respect to S and one with respect to S prime. And then setting the coordinates equal to one another. And this definition of the metric will assign the same distance to states that differ by an overall phase. So this is the Fibonacci metric. This is the one that I think is most commonly used in the literature, but you will also see the F1 cost function from time to time.
Let me pop in there again. If you had just the first term in there, it's just the standard induced metric. If this were a matrix Lie group, it would be the induced metric that you get from the embedded state. So the subtracting that second term, what does that do for you?
So that's the one that's responsible for cancelling out the contribution from the from the stationary solid. So that's the second term that cancels out this contribution. Exactly.
Okay,
So you're 100% right. So if you just like the first term, then again you would get something that's assigns a different distance to states different by an overall phase. But the
I mean, you have a U under your dagger, so the phases might.
so remember that you have the derivative.
The derivative. I see.
I think
Okay.
so that's the one.
Cool.
Excellent.
Cool.
But it's in the second one that cancels. Now, a thing that I want to point out, this is not often pointed out in the literature, but the key quantity that you want to compute actually is this overlap of S prime and S. So just as a reminder, that is this state over here. S is the state with the unitary parameterized with the coordinates S, and S prime with the coordinates S prime, so different ones. If you compute that 2-point function, the overlap of the S states and the S prime states, that is really the quantity that's sourcing these metrics for you. If you give me that, I can compute either of these two metrics by just applying these two formulas. The one just being a derivative of that overlap, and the other one being the derivative of the logarithm of the overlap. And that's really the quantity that's important. And in a lot of the work that we do, it's computing this overlap that we're really interested in. Now, the logarithm in this case, so like you had the second term cancelling that overall phase contribution, it's now the logarithm that's doing that. Because the logarithm will just drop down the factor that's just S dependent. I take a derivative with respect to both S and S prime. One of those derivatives will kill that contribution. So that's a nice way to see that that's work. Right. Right. And because of that also, your states need not be normalized. If you work with unnormalized states in this Witwatersrand study metric, any normalization will fall out due to similar reasons. Now, one other instance here that's important is that if you have states that aren't parameterized, you can parameterize holomorphically. So as opposed to 2 in real coordinates, I can specify in complex coordinates. Then you can actually substitute in this formula for the Witwatersrand study metric, where I take a derivative with respect to the holomorphic and anti-holomorphic coordinates, and there's no longer the need to set S prime equal to this. So that's one of the nice features if you have a manifold of states that can be parameterized in this way. And some of the examples I'll show you shortly, this is exactly what happens. Right, now, another thing that I just want to point out also is that the Witwatersrand study metric comes up in another context. So those of you that are not familiar, it's work by Ashtekar and Schilling, where what they essentially try to do is formulate quantum mechanics in a geometric way. What happens there is that there is a natural metric that occurs that you need to introduce, and there's a natural symplectic form that you need to introduce, and that's what you get for them. Also, again, the quantum state overlap is important, and in fact, the metric is exactly the Witwatersrand study metric that we've introduced previously. So that's why it's a very natural choice. So when you're describing these quantum evolutions in a geometric way, it's a very natural metric to come up. And what's also nice about these manifolds in this case is that you can describe any transformation, any operator acting on the states by means of vector fields on this manifold. And the vector fields here are related simply by derivatives of these overlaps of your generator contracted with the symplectic. This now gives you a vector field in the manifold, and this captures all the possible transformations of this. So it's a very nice description, just as an aside. So I need to get to some examples just to make things a bit more concrete. So let's start with low rank algebra. So a rank 1 algebra, and I'll have a single Cartan element, L0, and I'll have 2 ladder operators, L plus and L minus. So examples of these are issue 1.1, issue 2, and the Heisenberg-Weyl algebra. And so the general group element you can write down is that one over there. I take all the Hermitian combinations, L plus, L minus, I, L plus, minus, L minus, and L0, and exponentiate them with some real parameter. That now gives me the group element. 3 generators, so a 3-dimensional group. So 3 continuous parameters. Now, using some formulas called Baker-Campbell-Hausdorff formulas, you can factorize any of these group elements into this form over here. So you can factorize it so that all the up ladders are to the left, the Cartan elements in the middle, and the down ladders are to the right. Now, these coordinates aren't independent, so you started with a 3-dimensional or three continuous parameters. There's one complex parameter Z in that case. And now there's two other complex parameters, but three of the real components of them are fixed in terms of Z. And if I recall correctly, the real part of rho 0 fixes all the dependency in that expression. Now, what's going to happen? So, to specify my manifold of target states, and how do you give you a reference state? Some reference state I'm going to act on in order to generate more possible target states. Suppose you pick the highest weight state. So, the highest weight state, the lowest weight state is the one that's annihilated by the down level operator, and it's an eigenstate of L0. So, if you look at that exponential in 16 that you have, I'm going to act with the exponential of rho minus L minus. Well, that's just going to be the identity. So all higher order terms are going to cancel. The second term is just going to give me an overall normalization of the state. So factor in. And I'm just going to be left with ZL plus on the reference state. So it simplifies this expression 17. Now I've got a manifold of states parameterized in a holomorphic way. Single complex parameter parameterizing this manifold of states. And maybe just also to point out, you had a stationary subgroup of the highest weight state that was L0. So L0 here is H, and that's a one-dimensional subgroup of the group of this three-dimensional group. So I should expect to have my three real parameters reduced by 1 to 2 real parameters or 1 complex parameter. So everything is nice and consistent. Right, but now that you have the state that's holomorphically parameterized, and there are some simplifications that come in, the key quantity to compute is this overlap. So that's the overlap that you can compute. I've introduced a form factor here that captures these three different choices that you could have. So for issue 1,1, the form factor F will be 1. For issue 2, it will be -1, and for Heisenberg value, it will be 0 in this case. Well, you need to expand around it to 0 to get the right expression in this case, but this captures all of these choices that you can make. That is the overlap that you can compute. And now you can go ahead and compute the fidelity study metric using the formulas that I cited previously. This is the metric that you obtain. You can compute the scalar curvature, and you find it's a constant scalar curvature. It's a two-dimensional manifold. For issue 1,1, it's a negatively curved manifold. For issue 2, it's going to be a positively curved manifold, so like a sphere. And for Heisenberg value, it's just going to be two-dimensional flat space. This is the metric. And this makes sense because of issue 2 is compact, so you would expect something like a sphere. Issue 1,1 is non-compact, so you would expect something that's hyperbolic in this case. Right. So, and the metric that you get here is exactly that of the Poincare patch, if you look at issue 1. Right. Now, so this is what I've demonstrated here is, just simply in terms of these manifolds of target states. But now, what if you have some time evolution operator? How is that going to act? Well, the time evolution operator is one of the elements of the Lie group. So this is some vector field on a manifold. So you can expect that there's going to be some flow associated with it in the manifold. And you can compute it for this particular choice of Hamiltonian, or plus or minus. Again, do a Bagel-Campbell Hausdorff decomposition. You can get an explicit formula, and this will now give you some path on this manifold of target states that the time evolved state will be moved by as a function of time in this case. And there's some nice properties that we'll discuss on Friday related to whether these paths are elliptic, if they're hyperbolic or parabolic, and what the physics are associated with this. These different classes of paths correspond to different features of the Hamiltonian during the time evolution. Any questions at this stage? Quite happy. Excellent. So just as a slightly more involved example, let me just study the Schrödinger group, also sometimes called it's a subgroup of the Jacobi group, where you have, again, you have these two ladder operators, L plus or minus and L0, but you also have two other ladder operators, little L plus and big L plus. You can realize them explicitly as big L plus is going to be like an A dagger squared, big L minus like an A squared, and little L plus, little L minus like A dagger, A respectively in creation and annihilation operators. So think of this as the group underpinning all linear and quadratic terms that you can build with creation and annihilation. Again, you can decompose this group using Baker-Campbell Hausdorff formulas. Again, you can act on the highest weight state, some nice simplifications, get explicit formulas for this overlap, and compute the metric. I'm not going to run through the details, but these can all be done very explicitly. And this is the metric that you obtain. It's no longer one that's maximally symmetric, constant scalar curvature though, and computing geodesics on this will give you the complexity. Right. As a last example, that I think, well, certainly has a more application for people looking at the holographic models, certainly, is conformal field theories. So consider, for example, SO 2,3. This is the conformal group in 3 dimensions. There are 10 generators. You've got the dilatation, 3 translations, 3 rotations, and 3 special conformal transformations making up this. Your primary states are the ones that are annihilated by the special conformal generators and have a definite scaling dimension. And for example, if you study one that is not, I'm just checking if okay, I did include the spinning case, that's great. So you can have primaries that have a scaling dimension delta and the spin J. And these are sort of the formulas that define the properties of that state. Again, you can take an arbitrary group element, decompose it using Baker-Campbell Hausdorff in a nice way, so that all the generators to the right of the translations, they actually annihilate state, and you're just left with this holomorphically parameterized. Let me just again say why this makes sense. So here I have a 10-dimensional group, and this is reduced to a 7-dimensional group in this case, because you have the special conformal generators that annihilate the state. Or rather, no, you have the stationary subgroup is the dilatation and the spin. So you should expect a reduction of 2, so from 10 dimensions to 8, and you get these 4 complex coordinates, so that's a total of 8 parameters. So again, everything nice and consistent. You can compute the metric in this case. So the metric is quite interesting. From the non-compact generators translations, you get this hyperbolic part of the metric. I haven't written the metric here explicitly, but it's a simple exercise to do it from this overlap. But that first term over there is going to give you something that's that's hyperbolic, so non-compact in the z direction, whereas the second term over here is going to give you something that's compact, so like a sphere. So you've got this interplay between a hyperbolic geometry and the sphere geometry, and again, the geodesic distances of this will give you the complexity of the state. And there was a question earlier on the representation. Note that the value for the spin and the scaling dimension that you specified plays a key role. So the prefactors that are going to come with that hyperbolic part and spherical metric are proportional to these numbers. All right. Are there any questions on Nielsen objects? This is I wanted to get to about halfway.
So clearly, these games do depend on the starting states that you put in there. Does this affect the applications that you have in mind?
So the good thing here, and maybe this might be in the notes, but I forgot to mention it. So what these coherence, or what these states are, these target states are actually what are called generalized coherent states. They were studied by Krylov in the 80s, and there's an excellent book by Gilmore also on this. I think they have 2 slightly different formulations, but it's the same idea that you can associate with an arbitrary V group some set of coherent states. One of the properties of the coherent states is that they give a resolution of the identity. It's an overcomplete basis, so there's some form factor coming in that resolution, but they give a basis for the full orbit space. So in that sense, you can use these tools for any, there will be some adjustment needed, but you can use these states for that orbit space throughout. Absolutely. So you can always express an arbitrary state in terms of these coherent states, these highest weight states that you start acting on. So that's why that's important. And in fact, these formulas and these Baker-Campbell Hausdorff formulas, these are all standard kind of tools when working with these generalized coherent states. So you may be familiar with the Glauber coherent states. That's e to the z a dagger acting on the reference state. It's an eigenstate of A. That's a special example of the generalized coherent states, where you've worked with the Heisenberg violons. But you can do this for an arbitrary algebra. And the main idea is just essentially the way we've set up these target states. You have a particular state, act of all group elements on that state. And this now gives you the set of coherent states. The resolution of the identity is essentially guaranteed due to Scher's. So you can prove using Scher's lemma that these will give you a resolution of the identity. If I integrate over it, I get something that commutes of all group elements must be proportional to the identity. Excellent. And this idea that the target states is the manifold of coherent states, and that they know one-to-one correspondence is actually something I'm going to use in the second part as well. When we study spread complexity, it's also my idea. Yes.
So in the beginning, we were talking about complexity as how many unitary gates you need to go from one
Yes.
state to another. Here are you talking about complexity in the sense of how far away group elements are living from each other in the manifold.
100%. You can still think of that in a sort of, slicing up that continuous unitary into many small unitaries. Still think of it in that strict way, but yes, the proper way is to think of this as on the group manifold, a non-identity element connecting you to the target state, and there's some distance associated.
So maybe also in the context of maybe like unitary gates, for example, in a quantum computer, applying on your state. In a practical example like that, are there any kinds of physical restrictions in terms of what actual gates you can create? Because this is obviously a bit more of a theoretical approach, but
Absolutely, yeah.
in practice, are we restricted on the kinds of operations we can apply?
So I'm not too familiar with the manufacturing of these gates, to be honest. Some of the students in the back might know a bit, or John, I don't know if you have any comments on that. Not sure.
I mean, I would imagine that you could create a single gate which corresponds to any operation you want, and then in theory, you could always come up with a single operation that will take you from one state to another if you engineer the gates properly. So this is really saying, given some constraint on the gates that you have, what's the complexity of getting you from one state to the next? Having a gate which has been specially engineered to go from one state to another may just not be very useful in a quantum computer.
Yeah, I mean, I don't know the literature that well. I know that in a quantum computer, you want to get a smaller set of gates with which you can build any operation that you want. This universal set. Yeah, but the manufacturing of these are too theoretical.
That adds all manner of things to the issue, right? Because then you can't go geodesic distances. Then you have to go zigzags, and that might mean even if you minimize the type of operations you have, you might actually force yourself into longer paths and whatnot.
100%. I should also comment there that the choice of continuous here, I think, is highly motivated for simplicity's sake. Working with discrete operations is a much harder problem than a continuous one. So probably there's a decent way to approximate the answers using these continuous tools, but it's probably that's the best that you can do. I would imagine. Right, so the second notion I just want to introduce, and this is really the one that I think most of our work has been built on over the last couple of years, is spread complexity. So what I introduced in the previous section is Nielsen complexity, and this is true for any choice of the group that you have at your disposal. But the problem is that the quantities that you're interested in may not be neatly packaged as elements of some Lie algebra Lie group. So say, for example, you choose a Hamiltonian that's not an algebra element, but an element of the enveloping algebra. Now it's suddenly, now it's difficult to have a gate dedicated to sort of time evolution. So in the last couple of years, there was, and also it's an ambiguous thing. This choice of gates, which is the appropriate set to choose? Which do you have at your disposal? This is not always clear. Spread complexity came about in the last couple of years as a way to circumvent this less ambiguous notion of complexity. And the idea is the following, that you only have two operations at your disposal. Time evolution, doesn't matter what the Hamiltonian is, it can be an element of some symmetry algebra, it need not, and superposition. All the states you can build with those two operations, that's now my set of target states. And so you again will have some reference state, so typically simple state. I can act with any combination of the time evolution operators I want. So a basis for all the states you can generate is given by this ON. Take the Hamiltonian to some power acting on the reference state, and this will give you the basis. This basis will not in general be orthogonal. In fact, I think it's always guaranteed not to be orthogonal. So you will have to orthogonalize this basis first by means of a Gram-Schmidt process to get this so-called Krylov basis. So we've used the inner product between these states, do this orthogonalization process, and obtain this Krylov basis. Now, the Krylov basis is an orthonormal basis for the Hilbert space of target states that you can access. The Krylov basis vectors you should now think of as an ordered basis in increasing complexity. Because to get the nth Krylov basis vector, I needed to act with the Hamiltonian at least n times. So in terms of the time evolution operator, I needed to evolve for a sufficiently long amount of time to start seeing that term appearing and to isolate it. And that is a more expensive process. So a way you can now assign the cost function is to take the overlap of your target state with these Krylov basis vectors, and there will be some number Cn, an increasing number specifying what is the complexity of that state. So I know it's more complex, how much more complex? Typically, choice of linear is made. So you're saying that there's a linear scaling in complexity, but it need not be linear, can be quadratic, can be cubic, can be exponentially more difficult, whichever you want to choose. But the choice of C is equal to n is often made. And the reason is that the Hamiltonian is actually tridiagonal in this Krylov basis. This is something that you can demonstrate. The Hamiltonian acting on the Krylov basis vectors give you a tridiagonal structure to the Hamiltonian. These coefficients that appear over here are called the Lanchas coefficients. ANs are the diagonal ones and the BNs the off-diagonal ones. And what this is now effectively done in terms of the Krylov basis vectors is take your arbitrary Hamiltonian and map it to a nearest neighbor spin chain with some coupling constants coupling these different sides, starting at 0 and moving all the way up to the dimension of the space in this case. And what that cost function there is then going to tell you is the average distance that you've traveled along the Krylov chain. And the choice of Cn is equal to n tells me what's the distance that you've gone. But it's a probability distribution. Any of the higher moments make a sensible choice for the construction in this case. There's a nice diagram that was developed by Balasubramanian et al. In the 2018 paper, where you can sort of visualize this hopping taking place with these Krylov basis vectors. So you want to compute a quantity known as the return amplitude, this quantity over here. Like we have for the two-pronged function in the case of Nielsen complexity, this is the key quantity sourcing everything. If you can compute that return amplitude, you can compute any quantity you want with respect to the Krylov basis vectors. And you can think of this as a hopping on this lattice, where you want to take any path going from the bottom node and again returning to the bottom. And the sum of the paths that you have there, so the red here is a hopping. So you're going to go from K0 to K1, that's in the first row, 0 for the first row, go to the first row, and then back from the first row to the second row. So that is a kind of path. Those are two paths taking you at the second level back to the lowest row here. And then you can just sum up these different paths in order to compute this return. It's one of the algorithms that you can use to do that. What's also notable is that the probability amplitudes, these phi n's, they satisfy a Schrödinger equation with these nearest neighbor amplitudes. So if you know the Lanchas coefficients, you can also solve them. So you need not compute the return amplitude. If you're just able to compute these Lanchas coefficients by means of usually some recursive algorithm, that's also sufficient information. And you plug it into this Schrödinger equation with this boundary condition over here. That boundary condition is just saying that at time is t is equal to 0, I'm at the reference state. And then you can solve that Schrödinger equation to get the probability amplitudes, plug the probability amplitudes into the cost function to get the complexity. Here are just some examples of these moments of the return amplitude written in terms of these coefficients. So they can be expressed entirely in terms of it.
Just the second way is the N in 31 on the right hand side.
The 2, 1. Oh, goodness. That one on the left-hand side should be an N. My apologies. Yeah. The return amplitude is the expression on the right-hand side. That's phi 0. Phi 0 of t is the return amplitude. That's the quantity you want. But the probability amplitudes will be, should be
K naught to K.
Exactly. Exactly. So, bit of a typo there. My apologies for that. Right, so, but the point is again, like we had for Nielsen complexity, it's again this particular 2-point function that you want to compute this return amplitude. There's some properties that are interesting. These are general statements that you can make. If you have a symmetry of the Hamiltonian, so you have some unitary, well, in fact, it need to be a symmetry. You make a unitary transformation of the Hamiltonian, then all that's going to happen is the Krylov basis will pick up the same unitary transformation. So your Krylov basis will just change like that. This does not hold in general for similarity transformation. So don't actually have that. So if you do something like transform the reference state with some finite temperature, you can expect to see different results. It's not going to hold in general for that. But if you have unitary transformations that commute the Hamiltonian, and you choose a reference operator that you acting on the reference operator gives you an open phase type of operator, then the evolution will be entirely contained inside the symmetry set. So in general, symmetries will decrease the complexity that you can see. The more symmetries the set has, the smaller the complexity. And like we did in the Nielsen complexity, you can compute the, here's just some examples that you can compute exactly. So for that rank 1 algebra, you can go through the exercise. And what you find actually is that the Krylov basis is just the highest weight state, active the ladder operator in times. And that will give you the inf Krylov basis vector in this case. And you can compute the complexity exactly. I'm just going to skip through the details, but you're welcome to have a read through it in the notes. But you can get an exact expression in these rank 1 algebra cases for the complexity. And that's what it's given. So the way to interpret that expression is you start off not on the highest weight state, but some coherent state, set 0, and you want to compute the complexity of the state Z. And that is what you'll get. So there's going to be some number assigned to each of the points in this manifold of coherent states in this case. Right. How much time do I have? Okay. I think
Whatever you need.
I could probably wrap up in the next 5 minutes. Just one property that I want to highlight that's still, I think there's still a lot more to understand here, but this is just an example that illustrates some misconceptions that some may have on this. Suppose I give you a tensor product Hamiltonian. In the Nielsen case, a tensor product will just mean that I have my manifold for the one copy of the tensor product and the manifold for the other. The geodesic distance will just be the sum of the two. Simply, geodesic distance will just add up. What happens in the case of spread complexity? Now here it's a little bit more involved because we're going to activate the Hamiltonian in times, and then we're going to formalize it. This gives rise to a non-additive feature of spread complexity on the tensor products. And the simplest way to illustrate that is just to consider a spin half representation of issue 2 cross issue 2. So on one Hamiltonian, the states are just plus half and minus a half, and similarly for the second. I take a tensor product of them, and this is the Hamiltonian I have. I have alpha 1 times the up ladder and down ladder operator for the one spin, and alpha 2 times the up ladder and down ladder operator for the second spin. Based on the previous example, where it was just the up ladder operator acting on the reference state, you may make this as a guess for the Krylov basis. Just act with the up ladder operator n times the Krylov basis vector. But this is not how it turns out. So here is the Krylov basis that you actually obtain. You can see that the first 2 Krylov basis vectors follow that pattern. Start with the reference state, active the up ladder operators once, active the up ladder operators twice. It's fine. But you actually get a third Krylov basis vector as well. And that is the orthogonal vector to K1 in that case. We've acted with the basis vector once. So in other words, you have the state, half minus a half and minus a half a half. Previously you had a sum of them, now you have a difference. The other orthogonal component. And that's now a more complex state. That comes due to the fact that I'm taking superpositions and orthogonalizing. And then because of that, if you were to just restrict to the first couple of Krylov basis vectors, it would still be additive. But due to the presence of that third guy, it's no longer additive. And if you were to plot the complexity, I'm just maybe going to skip over this first section because you can ask questions about how accurate is the approximate Krylov basis. If you were to plot these complexities, this is what you find. So this is what I've plotted here at the bottom is the complexity of just, the complexity for the one qubit and the second qubit. And then on top of that, the Krylov complexity or the spread complexity of the system, taking all of them into account. And due to that third Krylov basis vector, you can actually see that the complexity is always higher than just the sum of the two. It's this additional contribution that you get that plays a role. And so this is a common misconception that you will see that it's just the sum, it's not just the sum. What you can prove is that if you take a tensor product of many systems, so say I have a total of n tensor products and I take n to infinity, what's going to happen then is that initially you can see that these two complexities line up quite nicely. And there's a particular time scale associated. That time scale scales with n. If you send n to infinity, that goes all the way to infinity, and they actually match up quite nicely. But the point is, you never see this regime following that time scale. You cannot access it if they get the n goes to infinity. And this is just something I want to point out. This is still something that we're thinking about. Are there nice tools to compute things away from these thermodynamic limits? I think that's maybe a good point to wrap up. I just want to make the last few comments on. So I've told you what complexity is now. So how can one apply it? Where does this show up? So there are two main fields of research where it shows up. The first is in holographic models. In fact, the original motivation for complexity came from the study of black holes in holographic models. And there's this very nice example called the Fermi-field double, where you have two copied systems, and you can create with entanglement a wormhole between these two. And what you can show is that even though the system's at thermal equilibrium, there is a wormhole that's growing between the two sides still. Another point is that, temperature doesn't change, so all the thermodynamic quantities doesn't change, but there's still something that's dynamical. And one of the ideas put forward by Susskind is that that quantity can be complexity. Complexity is the quantity that, so there are many states that are still at the same temperature, but they can have a different complexity, sort of a more fine-grained thermodynamics if you want states. So that's the one avenue where it has been applied. The second has been in quantum many-body systems to diagnose all sorts of features. The most developed literature is in chaotic systems, where you can show that if you have a chaotic system, then complexity will grow exponentially. There's a bound on how fast it can grow, and there's some relation to the growth for another diagnostic of quantum chaos called the unstable code. There's a relation between those two. There's this triple inequality between them. Besides that, we've also made use of complexity to diagnose things like topological phase transitions, PT symmetry breaking, and so on in quantum systems. I hope to tell you more about that on Friday, but these are just some of the applications there. So, quantum many-body systems and holographic ones.
Thank you. Thank you very much. Any other questions that have not yet been thrown on the floor?
I might not be understanding properly, or I might have missed it, but it seems like you've defined many, you have many sort of complexity measures.
Yes,
So many ways to define complexity. So which is sort of, I suppose, is not a best measure of complexity, which is in what instances is so for what scenarios is would some complexity be applicable when others be applicable?
No, that's an excellent question. I think ultimately the answer is that complexity is just from its definition a very ambiguous quantity, because you need to specify cost function as well as the set of operations that you have to dispose of. The best you can do is a natural design. What's the most natural choice that you can have? Complexity. I think spread complexity is probably the closest that you can get, because It's a very simple quantity, can be defined for any unit. One point that I should also point out is that this Krylov basis, you could have said that, well, this is a particular choice of basis that, you've arrived at this basis by this normal procedure. You could have chosen any basis you want. And there's a very nice theorem that was proved a couple of years ago that the Krylov basis is the one that minimizes complexity for the time involved in different states. So that's the argument for naturalness for the Krylov basis. So in that sense, but certainly complexity is a highly ambiguous quantity. And I think if you choose the gates in a particular way, cost function in a particular way, you'll probably diagnose all sorts of properties of the system. But with great complexity, you're more constrained. The question is, what does that mean?
Okay. Yes.
I was just wanted to clarify that thing that you say we take to infinity, is that the number of gates?
So that would be in the tensor product system. So think of this maybe as a spin chain, with n lattice sites, and I take the number of lattice sites to it. So that's like a mini particle in this case. And in that case, you get a big simplification.
Sounds like a continuum limit now.
Yes.
Does any continuum limit simplify things like that?
That's a great question. I'm not sure. I'm not sure. I would suspect that there would be some simplifications, but I'm not sure. I'm not sure.
My brain is calculating through a completely different realm at the moment. I'm talking about thinking a lot about Monte Carlo generators for certain experiments, right? Where you have time evolution, essentially this quickly model, then you put more and more particles into your final state. You grow the complexity of the representations that you get. Right? You get more and more complicated sub-representations, all tied into an overall color singlet, but the number of color singlets goes up, right? Like crazy. Where you have more particles. And at the moment, people are largely limited to the large and C limit, with a few attempts going beyond that. Now, I think it would be interesting to think about this from a complexity perspective in a particular way. Maybe this tells you something about how things should grow, what you would expect. So, but okay, right. Totally different game. We are continuous, but we are, on the other hand, we are discrete in terms of representations that we form.
Yes. So definitely that problem can be phrased in this language, but in terms of how when it simplifies, then I'm not sure. But that could be really interesting.
Maybe we should talk about this offline.
Definitely.
You have another one? You were raising your hand.
Yeah, but also on that note, this may be another basic question, but can you sort of define complexity on any quantum system, like even the simplest one, or let's say like an infinite square well?
Absolutely. So spread complexity you could certainly define in that one. Nielsen complexity you would have to, again define some set of gates. So the question would be: you have a set of gates. Can you access all the states that you would access by time evolution? So is there a set of gates that can represent time evolution in the set of gates? That's not guaranteed. Spread complexity, that's guaranteed. Absolutely. Yeah. Absolutely.
We have more questions?
This is now following on that. I think that are there not systems where the gates that you have, these unitary transformations, are not just the time evolutions that form the Krylov basis? Like,
absolutely. Yeah. So you can have you can certainly supplement that with calculations as well. So also. So as I said, the way to think about spread complexity is you just have these two operations, but there's scope for generalization of that as well. So you don't just have time evolution, but so time evolution with different operators, or some sort of rotation or translation. So absolutely.
So you have
variety of different cost functions that you can choose. So complexity is kind of a moving target in its definition, but what exactly do you gain by thinking about different cost functions in quantum mechanics? To me, it seems a bit weird, or I don't see what you would gain from that.
So what you ultimately want to do is diagnose particular features of quantum systems. So for example, if there's a transition from integrable dynamics to chaotic dynamics, you want a quantity to compute that's going to give you information. So one quantity that you could compute is the speed form factor. Compute the speed form factor of the system, and that will tell you if you're chaotic or not. It's been shown that with complexity you can diagnose the same thing. I suppose it's just a question of which will be simpler to compute. With spread complexity, there is this iterative algorithm. It has its advantages. So it might be simpler in some instances to compute that. And it's also been shown that there are topological transitions that you can compute with complexity. They're typically quite difficult to diagnose. There's some topological transitions. One example is the dive chain, which is this spin chain with nearest neighbor coupling, and it also has a term that looks like a superconducting. There's a topological transition that takes place there, and you can use spread complexity to determine that. So that's one of the meetings. But yes, certainly, it's the questions I had at the beginning was exactly this of what can you compute? How should you choose your gates if you want to diagnose a particular problem or particular feature? These are all still very much open questions.
It kind of seems to me like this complexity, at least in spirit, there's a bit of analogies to something like entropy. Is there a relationship there? I mean, because just in terms of when you were saying, oh, there's a bit of an ambiguous definition, but like for entropy, there's something similar where it depends on how you define your macro states, but then you still have this sort of law which tells you that entropy will, it tells you how it progresses. So there's something similar.
So the work there's actually works by Susskind that works on that analogy. So it's got something like where you have the three laws of thermodynamics. It has these three laws of quantum complexity. Well, they're a bit a typical Susskind cell. It's not very rigorous, quite loose, but there are some ideas certainly out there. I should say that what you get with the Krylov basis here is a probability distribution. You can define something like a Shannon entropy like function using that. And there are some conjectured properties of this. I don't know how close that's been brought to really interpretive, but there should be. We expect there should be some relation, and there are some ideas.
Everybody totally informed and absolutely in the clear. All right. He's not far away, right? Should clarity disappear as you start thinking about this again? He's easy to reach.
Absolutely. I can maybe give my email address as well. That will be helpful. Right. So if you want to get in touch, you can put me an email. Alternatively, I'm in the maths building currently in the laboratory for quantum gravity and strings. So if you enter the maths building, right hand back corner of the first floor. So yeah, please feel free to
So let's thank him again. And I hope to see you guys all back on Friday.